Who is the music nerd? Is it me, with years of experience listening to music? Or is it a $35 computer running neural network? Today, we are testing a brutal question. Can a Raspberry Pi recognize a music genre out of 1 second of audio? And can I? I trained 2 different AI models. We will tear them apart, test for accuracy, and then battle live. Welcome back to my channel. My name is Kasia, and today we will see some music. The goal is to set up a digital listening booth. The system needs to capture a slice of audio, process it, and categorize it into genre like rock, jazz, disco, or classical. And the key constraint here is time. Now, doing this on PC is easy, but doing it on an embedded device is a completely different beast. But before we get to the fight, let's choose our weapon. And which AI architecture is best for the sound? To follow along, you will need a Raspberry Pi 4, cooling solution, power supply, micro SD card, monitor and micro HDMI to HDMI cable, mouse and keyboard, and headphones. Now you can play the music and capture it with a microphone connected to Pi, or just input the file. I needed to do that during the science fair as it was too loud and impossible for the Pi to capture the music and distinguish it from the background. It was difficult for me as well. To build this, I started where everyone starts, the TinyML cookbook by Gianmarco Iodice. The book uses Raspberry Pi Pico. The example of music uses something called an LSTM, a long short-term memory network, which is a recurrent neural network. Some areas where RNNs have been found very successful include neural language processing, time series analysis, and speech recognition. Logically, it makes sense. Audio is a time series data. But then I started digging into some research, and there is a challenger. It's a CNN, Convolutional Neural Network. Now, you're probably thinking, wait, CNNs are for computer vision. And here is a secret sauce. We don't use raw audio files. For both LSTM and CNN, we will first convert that 1 second of audio into a visual representation called a spectrogram, and then to something called MFCC. Think of it as a heat map of sound. Low frequencies are at the bottom, high frequencies are at the top, and time is on the x-axis. Suddenly, our music isn't a time sequence anymore, it's a picture. And CNNs are incredibly fast at scanning pictures. On the other hand, MFCCs still carry temporal information. In fact, the MFCCs are features extracted at a particular time step, thus great for LSTMs. So, I built 2 models. And today, it's not just us fighting AI, it's AI fighting itself. Before we can test, we need to talk about training. For this experiment, I am using the GTSAN dataset. GTSAN? How do you actually pronounce that? It is essentially the hello world of music genre recognition. It contains thousands of 30-second tracks split across the genre. We will use 1 second windows. This does 2 things. First, it drastically increases our dataset size. Second, it forces the AI to make decisions based on immediate context. We will follow our standard data flow you may remember from my previous videos. We need to do preprocessing, in this case convert the music to MFCCs. We need to make sure that you do the same transformation during the training and inference. Then we create the model, train it, convert, deploy, and run inference. I quantize the model parameters to use int8, but stay with float for inputs and outputs. The pipeline is similar to previous projects. We prepare the dataset, load, preprocess to MFCC, and divide into train, validate, and test. Then we create a model, train, visualize metrics, prepare representative dataset, convert to TF-Lite, and save. For For the LSTM model, I stuck closely to the architecture found in the TinyML resources. It fits the sequential data into a unidirectional LSTM layer, followed by some dense layers. It's a deep network, but it's narrow. For the CNN, I built a custom lightweight architecture. I used 2D convolution layers, batch normalization, max pooling. Then I flatten it and run it through the dense layers. Training them on my desktop, the difference was already obvious. The CNN trained faster. But the training speed doesn't really matter here. Inference speed does. Inference is when the Raspberry Pi actually makes a guess. Let's get to the technical weighing. This is where the results shocked me actually. I loaded both the LSTM and the CNN onto the Raspberry Pi, and the pipeline is similar to the previous projects. You need to copy the Python script and model to the Raspberry Pi and then install some libraries. What the Python script does is load the model, allocate tensors, grab 1 second audio or use the file provided as input, compute MFCC and run inference. We are looking at 3 metrics: size, speed and smarts, thus accuracy. First, the LSTM. This model is tiny. It weighs in at only 183 kilobytes. It is incredibly lightweight. However, when we look at the accuracy, the LSTM struggles. It stopped at 73%. Now, let's look at the CNN. It is much heavier, weighing in at 1.6 megabytes, almost 10 times larger than the LSTM. The inference time is slower. The CNN hit 82% accuracy. That is actually a massive jump in reliability. This brings us to the question: speed versus smarts. Is the CNN slower? Yes. But let's be real, it is still faster than a human being. And the refresh rate of your monitor is way slower, 60 Hz, which is 16 milliseconds. To us, it feels exactly the same, instant. Especially if you take a look at the MFCC calculation. Now, I was about to stop this video and start from scratch, but then I thought it might be actually an interesting learning experience. I performed the benchmarking on my laptop, including the TF Lite version, then on Raspberry Pi with 200 runs of the model, and as you have seen previously, the data was promising. However, when I wanted to try it competition style as promised, I realized that actually there is a huge issue. And it is coming from the MFCC calculations using librosa. So even though my inference is less than 2 milliseconds, the first MFCC calculation takes a few seconds. I didn't realize how big this issue is. In order to fix this, I would need to find a different way of MFCC calculations. One of the candidates could be using the CMSIS DSP library, and then I would need to follow the full chain and retrain the model. This shows clearly that embedded performance can force you to change your front-end and data manipulation. Model, the data, and the hardware are inseparable. I decided to continue with the video using the current calculation and proceed to competition. So for today, I am choosing accuracy. I am deploying the CNN. It is slightly heavier, but that 9% boost in accuracy is the difference. Time for the main event. The rules are simple. I have a dataset consisting of 1 second audio, which is not prepared by me. I will be listening, Raspberry Pi will be listening, and whoever recognizes the genre faster wins. Let's start. Classical. Hip hop or reggae? Not sure.
Down and way.
Pop.
You right.
Pop. Reggae. So, what is the verdict? In the competition human versus machine, Raspberry Pi takes the gold. We have seen that for audio classification you can use various models, and it is actually the preprocessing that can be a real bottleneck. It all depends on the goal of your project, and you need to analyze the trade-offs. The code for today is linked below. Thanks for watching, and see you in the next build.